Thank you, Alison. Good day to everyone online. My name is John Barker. I'm a solution architect with NVIDIA. Today I'm going to present the first module in our deep learning training series. Today's module will be an introduction to deep learning with GPUs. This module is intended to be for a complete beginner to deep learning, so we're making no assumptions about prior knowledge of deep learning or any particular academic prerequisites. And we will take, in today's class, a very practical overview of the applications of deep learning and how GPUs are enabling those applications. So the content for today's class will be this simple agenda. We're going to first cover what is deep learning. We'll then talk a little bit about the software frameworks that are available for developing deep learning applications. And then we will finish with a discussion of how deep learning can be deployed in different hardware design patterns. So, what is deep learning? Deep learning has become the most popular approach to artificial intelligence in recent years. So artificial intelligence is the quest to build machines that can perceive the real world, understand the world through sensory inputs like video, cameras, and microphones for audio. Currently, the focus of deep learning within AI is on specific perceptual tasks, and there are many successes, some of which we'll talk about. Some of the world's largest internet companies are deploying deep learning today for artificial intelligence machine perception tasks in both research and in production, and almost all of those efforts are using GPUs to accelerate the process of training the deep learning systems. Some high-level practical examples of where deep learning is being used today. The most common and well-known example is detecting and classifying objects in natural images, but also there is localization of objects within images, recognition of different types of activities taking place in videos, or understanding of the scene present in videos. In speech, there are applications on the transcription of speech, the translation of speech, and as well as natural language understanding. In automotive, there have been great advances on the detection of pedestrians, traffic signs, vehicles, and other danger indicators for automotive. And in medical research, there have been applications in medical image understanding, as well as data science applications for other types of medical data. So, coming back to the question, what is deep learning? The way I like to think of deep learning is that it's really an answer to the question, if you want to teach a machine to perceive the world, how would you do that? And the traditional computer vision and speech recognition and natural language understanding communities for really the last 50 years have taken the approach that's shown on this slide to that question, where raw data is passed into feature extraction functions, which attempt to extract features that are believed by the designer of the system to be important for discriminating different types of objects in the image, or different phonetic sounds in the audio, or different types of word in the text. And then those features are passed to a typically linear classifier or detection algorithm, which is sometimes a machine learning algorithm in itself, which then attempts to either detect the object, classify the object, transcribe the speech. The problem with this approach is that it's very difficult to design features that are reliable for detecting the objects you care about, are not are robust to natural variations in the presence of that object. So in the case of imagery, variations in lighting, translations in the image, changes in perspective. And so we typically find that these approaches have ended up with very brittle performance. They will fail on unexpected examples, test images, because of some of those variations I mentioned. So deep learning is really the modern approach to addressing some of those limitations of this traditional approach. And in the deep learning approach, we instead replace those two steps I described of a handcrafted feature extractor followed separately by a shallow or linear classifier or detector with a single model. The model here being this collection of green circles with connections between them, which we'll talk in more depth about what that is. And so the approach to having that model become an effective feature extractor and then classifier for your task is that you feed into the model large amounts of what we call training data. So typically this is, in the example here, these are images of animals along with the label for the type of animal that's shown in the image. We pass the image into the model, then we do what's called feed forward. It passes through the model, and at the end, the model makes a prediction as to what the animal is. That prediction is then compared to this ground truth label we have, and if it gets it incorrect, if there's an error, then that error is passed back to refine the model so that the performance improves next time it sees that particular image. And if we repeat this many, many times with perhaps millions of images, eventually the average performance across the images will be satisfactory for your task, and then you can do what's called deploying the model, where you take that model's parameters fixed now, and you push new images that the model was never trained on through, and hopefully it correctly classifies that this dog in the water is in fact a dog. The benefit of this approach is that no human needs to design what will be the important features for recognizing dogs or differentiating dogs from cats. The deep learning method will learn those features, and it will learn the right type of features to look for to be optimal for this task. So some examples to show how this generalizes. These are examples presented by Jeff Dean from Google at NVIDIA's GPU Technology Conference this year. And these are all examples of where Google is using deep learning in research and production today. So there's the example we just saw of images and the output being the label of an animal. There's audio and the transcription we see here, Seattle restaurants. There is web pages, web page documents, and a user search query, and the output is the probability that the user will click on that particular document. There's translation from one language to another, and there's even much more nuanced labeling of images. So rather than just the label of a particular animal in the image, we actually get a natural sentence that describes what's being seen. So this model I described, what is it in deep learning? Well, it's what we call an artificial neural network. This is a biologically inspired model. A biological neuron that makes up the brains of humans and other animals is a cell which is connected by many other cells through these branches called axons and dendrites. And this cell can send out electrical pulses which then excite the cells it's connected to, and if they get sufficiently excited, they will themselves emit electrical pulses. And once you do this in a very complex network, you can end up with very complicated feedback loops of activation. So the artificial neuron, is a very simple mathematical model of the biological neuron. We see an example of the artificial neuron on the right here, which is taking 3 inputs in this case, although it could be an arbitrarily large number of inputs that it receives. So x1, x2, and x3. So think of these as activations, pulses that are coming from some other neuron. It then applies a weight to each of those incoming activations, and then it sums them together and applies some nonlinear function to the resultant sum. So it's a very simple algebraic unit. An artificial neural network is a large collection of these very simple trainable units. When you form a large collection of these units, they can actually collectively learn through the training process I previously described very, very complex functions that map raw data to complicated output decisions. What we call these artificial neural networks are arranged in layers. In this chart, we see the layers of circles arranged vertically in a 3-dimensional representation here. The first layer on the left is called the input layer, and that will be where raw data, so image pixels, for example, are input. The final layer, where the classification is made, in the example we gave before, the classification of which animal is in the image, is called the output layer. And the layers in between are called the hidden layers. So where does this term deep come from in deep neural networks or deep learning? It comes from the scale of these networks. The mathematical formulation of artificial neural networks has existed now for many decades, but we are only in very recent years, in the last decade, seeing these very impressive applications emerging. And one of the reasons for that is simply the scale of network we can now build and train. So the deep term comes from both the fact that the networks we are building have very many layers of neurons, and each layer has very, very many neurons within it connected to very many neurons in the layer above. So a typical network today that would be used in a cutting-edge computer vision application like object recognition in natural imagery might have 10 layers and maybe 1 billion trainable parameters. Those parameters, that number 1 billion is a function of how many neurons there are and how they're connected together. So it's a complicated function to estimate the number of parameters in a network. And we might train that network on 10 to 100 million images, maybe even more. And you have some associated objective, like recognizing the animal or identifying a face. And this network may take you on a single GPU 30 days of processing to train, but we can bring that time down by using multiple GPUs and other types of training parallelism, which we'll talk about. At this point, I'll make a comment about why a deep neural network is so effective for these tasks. Why are we seeing these impressive applications? And the reason is that by layering these many layers of artificial neurons, we're able to learn what are called hierarchical feature representations. So we see on this slide at the top an example where our neural network is attempting to take images of people's faces and identify who is in the image. At the lower layers of the neural network, what happens once a network like this is successfully trained is we find that we learn to recognize very low-level, pixel-level features, so oriented edges, gradients of color, textures, that kind of thing. In the middle level, those low-level features are learned, significant groupings of those low-level features are learned, which indicate important mid-level features in the image. So, for example, eyes, noses, ears, and mouth. And then at the very high level, as you get towards the final classifier, those mid-level features are grouped together and important groupings are learned, which are able to discriminate different people, particular people's faces. The advantages of deep learning over the traditional machine learning method we described earlier, or machine perception methods we described earlier, is robustness. There's no need to design the features ahead of time. You don't have to have expertise, particularly in the data set that you're trying to train to get started, because the network will automatically learn what features in that data set are important for the task that you're trying to train the network to be good at. And for similar reasons, the network naturally learns robustness to natural variations in the data. The method is very generalizable. There's very little about the formulation of the network, the artificial neural network that I described, and the training process that has to be modified to ingest a different type of data. So the process for training a network on images and training a network on audio samples is very, very similar. And certainly different applications within those different data types are very, very similar. So it's very generalizable, and this means it's also a very scalable solution. If you have the infrastructure to build and train deep neural networks, you can very rapidly apply that infrastructure to many different problems. And one of the very elegant things that emerges is that the performance of the networks typically improves the more data you train it on. And the method is massively parallelizable. So these applications can be applied to web-scale data sets. One particular type of neural network that has become very important in recent years, driven by the computer vision use case that we talked about, object recognition in images being an example of that, is the convolutional neural network. Again, this is inspired by the structure of the human visual cortex. It's a very crude model of the human visual cortex, but it is inspired. And it's this neural network structure that allows this hierarchical feature representation for images to be learned that I described, going from low-level pixel features up to high-level abstract concepts. And the way these networks are structured is that rather than having a network like I showed before, where every neuron in one layer is connected to every neuron in the layer above, there's local connectivity. What this means is that the network can learn for images to recognize the presence of a feature, whether it be a low-level or mid-level feature, even if it's translated somewhere else in the image, or it's scaled or rotated slightly, or there's contrast variation. The image we see here on the left at the top shows a cartoon of the structure of a convolutional neural network. In subsequent classes in this series, we'll get into some more of the detail about what that structure actually looks like. But the important thing to think about here is that it's trying to learn this visual hierarchy of visual features, and we see some of those underneath that diagram of the network. In the first layer, the network learns the 3x3 grid we see is the network, the features that the network has learned. So we see some oriented edges, and then the larger grid of colored images are patches from the training data set, which maximally are activated by those features. And so we see, as we go up the layers to layer 2, we start to learn more complex, smaller shapes like circles, long, thin lines. And indeed, as we move to layers 3, 4, and 5 in this convolutional neural network, we learn higher and higher level features that are present in the image and useful for discriminating different types of images, until we're finally in layer 5 learning what dog faces look like and human forms look like and flowers look like. So convolutional neural networks are the leading approach to computer vision tasks. The current leading approach to natural language understanding makes use of another important type of neural network, which is called a recurrent neural network. The structure is very similar to the basic artificial neural network we described before. Here we see, if you like, 3 artificial neural networks side by side. But what we're actually seeing here is the same neural network, but it has a recurrent relationship from the middle layer, hidden layer, back to itself. What this means is recurrent neural networks are very good at learning sequences of data. They can learn a pattern that frequently appears in a data set, and then they can learn, when they partially see that pattern, to predict what will come next. The example on this chart shows the sequence of characters, hello world, being input 3 characters at a time, and the output that the network is training on is then the following 3 characters. A network like this would be very easily able to learn for many different such sequences of characters what common patterns of letters are and what usually follows when it sees a partial sequence of characters. So deep neural networks, both the convolutional kind, the recurrent kind, and the basic artificial neural network I described, have become dominant in machine perception tasks. There's a number of examples on this chart, which comes from Jan LeCun at Facebook and NYU. In particular, for computer vision, handwriting recognition, recognizing numbers in street view images, and then also for natural language processing and speech recognition. Again, deep neural networks dominate. So why is this? There are three driving factors. There's the availability of big data made available via the internet predominantly, and things like social media imagery uploads, unprecedented amounts of data available to train networks on, growing at an exponential rate. On the right-hand side, there is GPU acceleration. So that is very compute-dense hardware, which is very well suited to training these artificial neural networks. And there have also been improvements in the actual deep learning techniques. Many people will argue that those improvements to the deep learning techniques are less significant than the availability of the data and the GPU acceleration, because we are predominantly applying the same mathematics that's been around for several decades. But there have been some improvements that speed up training time and improve the performance of these networks. So now we'll move on to talk about the relationship between GPUs and deep learning. So GPUs have become the prominent platform for deep learning. There is a well-known computer vision contest hosted annually called the ImageNet Image Recognition Challenge. The format of this contest is that the organizers provide 1.2 million natural training images of the kind we see on the bottom left here, and they provide the labels for the objects that are in the image. And those labels come from 1,000 different categories of objects. The task is to develop an algorithm which can correctly label the objects in an unseen set of test images. Prior to 2012, performance in this challenge was around 25 to 30% error rate. And that was the top 5 error. So that meant that the algorithm would make 5 guesses as to what the object was in the image, and it would get it correct if any of those 5 guesses was in the image, and it would get it incorrect if the true object was not in those 5 guesses. And there was about a 25 to 30% error rate. Then in 2012, a team from the University of Toronto, a well-known deep learning professor called Jeffrey Hinton and one of his graduate students entered a deep neural network. It was a convolutional neural network, like we described, trained on GPUs, and in that 1 year, they improved the performance by nearly 10%. And this was unprecedented for the time that the contest had been running. And then since that, every year, there's been dramatic improvements in performance. And now, in 2015, the contest hasn't been run this year, but other papers have been published using the same data, and the performance is actually below 5% error. And this is 5% is a significant number because there has been some tests where a human volunteer has attempted to hand label the images, so do the job of the algorithm themselves, and they get about a 5% error rate. So the machine is comparable to human performance on this challenge. And correlated with the improvements in performance are both a massive increase in the number of deep learning entries and the use of GPUs to train those entries. And in 2014, there was 110 GPU entries, and I believe there was only one non-GPU entry in the contest. GPU-based accelerated deep learning is being used in a very large number of web-scale internet companies for all of the applications I previously described in computer vision, speech recognition, also in very many startups who are, again, across the board in terms of applications. So what is it about GPUs? Well, another example here of the effectiveness of GPUs for training deep neural networks. In 2012, early 2013, Google published a paper which was quite famous and spawned a Wired article where they used 1,000 CPU servers, each with two 8-core CPUs, and they trained a convolutional neural network with 1 billion parameters, and it learned from YouTube videos to recognize the faces of cats and the faces of people. And it's estimated that it cost Google on the order of $5 million to build that system, and it used about 600 kilowatts of power. Very shortly after, the paper that's in the box on the left here, the ICML 2013 paper, was published by the Stanford AI Lab, where they showed that using 3 GPU accelerated servers, each with 12 GPUs and about 18,500 cores, they could train the same network, achieve the same performance, but they would only use 4 kilowatts of power, and it only cost them $33,000 to build. So GPUs are very power efficient and cost-effective solution for training deep neural networks. Why is this? Well, I know we've only had a very brief introduction so far to how neural networks work, but the answer is that because the neural networks are structured from these very simple algebraic units, these artificial neurons, the same computation is being performed effectively very many times over the network with just a change in the activations that are input into each of the neurons. What this it emerges that then the mathematics of feeding forward a data sample through the network actually is predominantly matrix operation, and it's inherently parallel, and it's very hungry for floating point operations. These are all things that GPUs are very good at. So GPUs can deliver you the same or better prediction accuracy for training deep neural networks, faster, with a smaller physical footprint, and lower power and lower cost. An example experiment that we ran last year was training a network that won the ImageNet challenge in 2012 called Supervision, which is a fairly large convolutional neural network. We implemented it in a framework called Caffe. We trained it for 20 iterations. We trained it on both a Tesla K40 GPU and also on a CPU-based system using two 10-core Ivy Bridge CPUs. And we found that the GPU speed up was between 8.5 to 9 times for training those 20 iterations. The three examples we see here of 64 images, 128 images, and 256 images refers to a parameter that you have when you train these networks as to how many images you feed through the network at once. And choosing that parameter is a trade-off between speed of training and the memory usage of the network. But we found fairly consistent GPU speed up despite that parameter choice. So what does it look like to actually implement a deep neural network in software? The hardware and software stack for deep learning applications is that we need hardware on which we can accelerate the computationally expensive deep learning building blocks. We need system software drivers for that hardware. We need libraries which harness that hardware acceleration for the most computationally intensive parts of the process, and we need programming frameworks which make it easy to build and deep neural networks and manage your data and manage this training process. And then finally, on top of that, we can build actual domain applications like speech understanding, image analysis, or language processing. NVIDIA contributes to this stack in all of the areas shown in green here. Obviously, the GPU hardware we've described is the world's best hardware for training deep neural networks. On top of that, we have CUDA, which is the general purpose parallel programming toolkit for GPUs. And NVIDIA develops libraries, QDNN, CUDA Deep Neural Networks, and QBLAST, the CUDA linear algebra library, which are highly optimized for, in these cases, deep neural network operations, linear algebra operations on GPUs. And finally, at the top, there's a tool called Digits, which I'll talk about more later. In yellow, there are a number of deep learning programming frameworks that are developed, that have emerged from academia initially and have all become large open source projects. And we'll talk a little bit more about those now. Those are not developed by NVIDIA, but we work with those developers to help them make best use of the GPU hardware for accelerating those frameworks. So the three most popular frameworks today, in no particular order, are called Caffe, Torch, and Theano. They are more similar than they are dissimilar. They all allow you to define a neural network architecture, to manage data which will be used to train that network, to manage the actual training process, and then to deploy the network against new test data. The differences really are the interfaces that they provide you. In particular, Caffe, which comes from Berkeley University, is C++-based framework that provides a command line interface, as well as Python and MATLAB. Torch is now, that came from NYU, and is now heavily in use in companies like Facebook and Google, and but has a large open source contributor base. Uses a scripting language called Lua. This makes it slightly more accessible for making modifications to the structure of networks or adding new types of neural network layer. But it's still very fast because of a CUDA backend. And Theano is a purely Python-based deep learning framework. You can find out more about all of these frameworks at developer.nvidia.com/deeplearning, but all three frameworks are going to be covered in depth in the subsequent modules in this deep learning series with hands-on labs to help you familiarize yourself with them. The fourth framework I've listed here is of interest if you are particularly interested in speech recognition. It's not just a deep learning framework, it's a broader speech recognition toolkit with a growing body of deep learning functionality. We see under all of the three first frameworks, Caffe, Torch, and Theano, that they are integrated with NVIDIA's cuDNN. So what is the effect of integrating cuDNN into those frameworks? We find, based on cuDNN version 2, that taking Caffe as an example, in this bar chart we show the performance for training three very popular convolutional neural network architectures that are used for computer vision: AlexNet, CaffeNet, and GoogleNet. And we compare to a 16-core Haswell CPU using an NVIDIA Titan X as a GPU. We find that purely using GPU acceleration versus running Caffe on the CPU, we get about this 8 to 9 times speed improvement I described before. If we then also add in NVIDIA's cuDNN version 2 library, which can be used seamlessly transparently within Caffe, we find we actually get up to about a 16 to 17 times performance improvement. So what is cuDNN doing? Well, at a high level, the way GPU acceleration works is that you split your application code between the GPU and the CPU. It's not that we're trying to execute the whole deep learning application on GPU. What we typically find is that 5% of your application code accounts for about 80% of your code runtime. So with cuDNN, identifies that 5% of code for deep neural network training and accelerates that on the GPU, even though some of the code is still being executed on the CPU. And for deep neural networks, in particular convolutional neural networks, the code which accommodates for most of the execution time is this convolution operation, which I alluded to earlier, which is the local connectivity of neurons from one layer to the layer below, and two other functions called pooling and activations. You'll get to see, if you take the hands-on lab associated with this webinar, you'll get to see these functions implemented in the frameworks I've mentioned before. So cuDNN supports the frameworks to accelerate their deep learning training. Digits is an NVIDIA tool aimed at data scientists and researchers, which provides a graphical interface for Caffe today and in the future the other frameworks too. And this interface allows you to visually manage your data, visually manage the architecture of your deep neural network, monitor the training of the neural network to ensure that your model is learning, is gaining good performance against your task, your classification task, for example. And it's not what we call overfitting your task, where it becomes very good at the training data but very bad at previously unseen test data. And Digits will also manage systems with multiple GPUs. So there's two ways that happens. One is Digits will allow you, if you have 4 GPUs in your workstation, Digits will allow you to train 4 deep neural networks simultaneously, one on each GPU. Or in Digits version 2, Digits will help you accelerate the training of a single deep neural network by parallelizing it across those multiple GPUs. And you can find out more about Digits at developer.nvidia.com/digits. And the next webinar and hands-on lab in this series will be focused specifically on building and training a deep neural network for computer vision using Digits. So my last slide is about design patterns for deep learning deployment. What we see on this chart is that there are really 2 stages in building a deep learning-based machine perception solution. On the left, there's the development stage, which is the designing of the network architecture, the managing your data, and the training the network. We'll call that the development stage. And on the right, there's the deployment stage, where you actually want to take the learned neural network and put it into production somewhere. Typically, this development stage is the domain of the data scientist, who will be iterating over designs for the model, trying to improve model performance. And this is where it's a very computationally expensive process. So this will typically take place in a data center or on a high-powered GPU-accelerated workstation. But an elegant part of the deep learning solution is that even though there may be tens of gigabytes or terabytes of images used to train a convolutional neural network, the resultant model, even though it has billions of parameters, is just billions of floating point numbers, and will actually only be probably a couple of 100 megabytes on average. So that means that model can be pushed to the deployment side very flexibly. It can be put onto embedded systems, perhaps in an automobile or a cell phone, a smartphone, or it can be pushed to a production stream processing system back in the data center, or to a user's desktop who wants to run their own individual data samples through the learned model. It makes the model very easy to share across teams of data scientists too. And then there's a final aspect to this deployment workflow, which is that you have a feedback loop typically from your deployed production system, which passes back test cases, so images that the network perhaps classifies incorrectly, back into the data center for the data scientists to then refine the model and improve over time. So GPU acceleration is critical in the development stage in the data center, but also massively accelerates this deployment stage to get high throughput for production systems, whether they're embedded or in another data center. So that's all the deep learning material I'm going to cover today. Before I take questions, I wanted to present the follow-on sessions in this deep learning series. There will be office hours, as Alison mentioned, next week, where we'll answer any questions that we don't get to today. And then we will follow on with every couple of weeks with webinars and hands-on labs that will discuss the digit system and the three most popular deep learning frameworks. And then you can find more information about that schedule and the content of those courses at the URL shown on the slide. And I'll mention the hands-on lab before I start answering questions. The hands-on lab is available at nvidia.quicklab.com. The first lab is live now. It's called a Practical Introduction to Deep Learning. What you'll see in that lab is some more in-depth explanation of how neural networks actually work, and then you'll see a different type of neural network implemented in each of Caffe, Theano, and Torch for a different application in each case, and you'll get to see some of the power of neural networks, deep neural networks, and the effect of GPU acceleration. The lab is free until the end of this deep learning lab series, and it only requires a supported browser. You don't need your own GPU. It's all browser-based. If you all log on straight away after this webinar, you may find that you get an error message because of the number of users. There are limits on the total number of users, but we're working on expanding that number of users. So if you do get that message, please do wait a short while and then try the lab again. So at that point, I will start answering questions. So first question is a good one. If we go back to the very first example I showed of labeling the animal objects with animal images with the animal present, the question is, will the output dog be accompanied by some quantitative value of confidence? The answer is absolutely. Those final neurons that do the classification of what the animal is will return a number typically between 0 and 1, which can then for each of the possible animals that may be present, and then there's a further processing step which is usually applied, which actually turns that into a probability distribution. A question that's come up a few times is whether it's always the case that you have to have this labeled data and a huge volume of it. So there's two parts to answer that question. The first is, no, you don't always have to have labeled data. Everything that I've described today is what's known as supervised machine learning. So the supervision refers to the fact that you have these ground truth labels with your data. There's another approach called unsupervised learning. In that approach, your objective for learning is not how accurately can I guess the correct label, but it's some other function which quantifies how well your hierarchical representation of features is learning to discriminate different input data samples and recognize similar ones. So to give a concrete example, if a commonly used deep learning data set called MNIST is images of handwritten characters between 0 and 9, you can train a deep neural network in an unsupervised fashion to cluster those images based on the digit that is present. And you can do that just by trying to cluster things that are visually similar away from things that are visually dissimilar, even though you don't necessarily provide the labels. The second part of that question was, do you have to have a huge volume of data? Again, no, you don't necessarily. There is a method called transfer learning, which is where you take a network that has been trained on some other data set, which maybe is much larger than your data set, but not trained for the very specific task that you want to address. And then you fine-tune the weights that have been learned in that neural network to perform well against your much smaller data set. And this can be a very effective approach where you can take a network that was trained on perhaps the ImageNet, 1.2 million images, and then just fine-tune it for your particular set of 1,000 images which you're interested in. And if you are careful, there are some aspects that you have to be very careful about, but you can get good performance then against your smaller data set. There was a question about the applicability to regression tasks, not classification tasks. So what that means for those of you who don't have a machine learning background, in a classification task, which is the example I showed with the images of the animals, you're trying to classify the image into a class labeled by the particular animal present. In a regression task, you're actually trying to estimate some continuous attribute or a number of continuous attributes. Again, the deep neural network structure very easily applies to regression tasks. The final layer of neurons, when you calculate the error in the predictions made by that layer, you don't have to do an error that is how many classes does it get correct. You can instead do something like a mean squared error between the number that it predicts and your quantitative labels, and everything else about the training remains the same. And the question is, how does that stack up against simpler approaches? For simple problems, you're unlikely to see very much benefit. So if you have a small number of variables, variates, and you're trying to predict a single regression feature or a small number of regression variable or a small number, you won't really see the benefit of this method. Where you will see improvements over some of those simpler linear models is when you have a very large, complex data set and a large number of regression variables you're trying to predict. Basically, a rule of thumb is the harder it would be for you as a human to write a program to do that prediction, as long as that would take you a long time. But even if you can't feasibly see how you would write it, you may see more benefit from a deep neural network learning approach. There's a question, can deep learning be used without neural networks? No, it can't. The term, at least today, the term deep learning has emerged to refer to very large neural networks. There was a question as to what is the factor that deep learning has overcome compared to other machine learning techniques such as support vector machines. It's not so much that it's overcome any factor as it's united this process of feature extraction and classification or regression into one learned system. So both of those components, the feature extraction and the classifier or regression, are simultaneously learned to be optimal for the task. A technique like support vector machine is typically used with these handcrafted features first extracted and then fed in as the input data rather than raw pixels or speech or natural language. And in many cases, as soon as you do that, you have actually thrown away important discriminative information in the input data, whereas a deep learning approach can learn to recognize the presence of that important discriminative information and make use of it in the task at hand. Another common question which has come up is how do you decide how many inputs, neurons, and hidden layers you will have in your network? So collectively, we refer to those things as the network architecture. The answer today is that is more of an art than a science. In an ideal world, deep learning would also learn to optimize that network structure, and there is research going on today into how you would do that. The way that people typically proceed in practical terms today is that they start with a network which has performed well on a similar task previously, a network structure, sorry, not an actual trained network. Then they test that against their problem, and then they will make refinements to address either if the network is underfitting, so not performing as well as you would expect it to given the amount of training data, or overfitting, that is it's performing well against the training data but not generalizing to your test data. And you would refine from there. Those refinements really come in two flavors. There is kind of parameter search, which you can, hyperparameter search, which you can take a structured approach to, where you program your computer to automatically try different values of the network parameters and find the best performing parameter. Or you actually, often a more effective approach is that you then start to dig into the specifics of your data and think about which sizes of filter, what size of feature is most likely to be discriminative in the image. I'm not suggesting there that you go back to handcrafted features, but you can often spot choices you've made in your network architecture which are obviously going to be suboptimal for your particular data. Someone said, are recursive neural networks also used for deep learning? There was a brief slide on that, and the answer is absolutely. They're fast becoming as active an area of research as the convolutional neural networks, and they're particularly being applied to the speech recognition problem and the natural language understanding problem. A question that was asked was, can one optimize the connections to reduce the number of connections between the layers? Yes, you can. The convolutional neural network architecture we described specifically does that. It chooses to have local connectivity, so a neuron in layer 2 may only be connected to a patch of 25 neurons in the layer below. That's not so much that's not done with the goal of reducing the number of connections, but rather it's done to have the network learn these translation invariant features in the imagery. In terms of optimizing to actually reduce the number of connections just because you want to reduce the computational complexity or your training time, that's really very similar to the question I answered before about hyperparameter search and automatically trying to search for the best network architecture. Is there a recommended minimum size for the data set to use deep learning? There's no single number I would be happy to quote to do this. For images, if you want to train a deep neural network from scratch on images that are on the order of 500 by 500 pixels, so not huge images, you would typically want to have a data set that's at least in the tens of thousands of images, and usually the data sets that are used are much larger. That is very much a rough rule of thumb because it really depends on the task you're also trying to have the network learn to do. So if you have 10,000 images but you have 10,000 classes of objects that you want to detect, well, that won't be sufficient training data because you would only have at most one example of each of the objects. Whereas if there's only two classes, 10,000 could be a very large data set. Another issue which you have to take into account is whether your individual data samples are highly correlated or not. So for example, if you decided that you were going to take your training images from a video, frames from a video, well, you would want to make sure that you sampled them from a wide variety of videos which had different objects, different activities present, different lighting conditions, etc. If you sampled all your frames from a single video, you might end up with 1 million training images, but they might be almost identical, which would provide very low training stimulus. So yeah, it's a complex question to answer. Question was, can backpropagation be used in deep learning too? Absolutely. The training process I described early on, where you feed your training image through the neural network, you work out the error in your prediction on that training image, and then you pass back that error to refine the network. That is done today almost exclusively using the backpropagation algorithm and an algorithm called stochastic gradient descent. In the hands-on lab, you will get to train a network using those two techniques, and in particular in the piano section of that lab, you will see where backpropagation is actually used to work out the adjustments that need to be made to the network parameters in response to a network error. Okay. There's a question here that for the case of image classification and detection, convolutional neural networks are said to perform the best. Still not using the detector/descriptor approach, but rather simpler features. Is there a hybrid approach, or am I missing something? So typically, a hybrid approach purely for image classification will be suboptimal in the sense that whatever the handcrafted features that you choose to input along with the raw pixel data, whatever those features are, the convolutional neural network would be capable of learning those features itself. There's strong theoretical foundation for why that is the case. Where hybrid approaches have proven to be somewhat effective is in the case of recognition of object, classification of videos. People's initial approach to applying deep learning to video was to input to the neural network multiple frames of the video simultaneously, so if you like a cube of data, and the convolutional neural network structure very naturally extends to be applied to a cube of data rather than just individual frames. But when they compared that approach to taking the individual frames and providing some handcrafted features, in this case optical flow features, which describes the transition from one frame to the next, they actually found that that performed just as well, but was far computationally cheaper to train. So that's an example of hybrid approach. If you want to learn more about that approach, you should look up the sports 1 million data set and the work on video classification done with that data set. There is a question on will RCNNs get any treatment? RCNNs are regional convolutional neural networks. So those are convolutional neural networks that are used for computer vision tasks, but where in addition to wanting to just detect the presence of an object or classify a whole image, you want to localize where that object appears in the image. These are very important in many applications. For example, in the automotive application, it's not enough just to detect that there is a car in front of your self-driving car. You need to know where it is as well accurately. So RCNNs, I will pass those on as a content request for the subsequent labs. There's a question on how are visualizations of the feature space typically produced, and I guess I would answer a slightly more general question, which is a criticism of artificial neural networks and sometimes machine learning in general is that you can learn black box detectors, so they perform well, but you don't really understand why they perform well. So visualization of what is being learned is one great way of addressing that criticism and actually getting some insight into what is being learned. The way that those visualizations are typically produced is that any of the deep learning frameworks will allow you to, when you deploy the network, test an image through the trained network, in addition to just getting out the classification or the regression variables that the network is trying to predict, you can actually extract out the values of the activations of the neurons in response to that training input. And then those activations can be visualized effectively as images themselves. And for convolutional neural networks, what this allows you to do is in some sense see for a given image which areas of the image and which features in the image were most important for classifying that image. Digits, the NVIDIA graphical tool for training deep neural networks, which I mentioned earlier, provides the ability to produce those visualizations automatically just through a graphical interface. So I would recommend looking up digits if you're interested in feature visualization. There's a question on the hands-on labs and will they allow you to actually train a deep neural network. Yes, they will. They will start in the first hands-on lab today with the coding of the network and the preparation of the data sets being done for you, so you can very quickly get to the stage of training a network and seeing what that looks like. Although you are free to modify during your lab, you're free to modify the network as well to see the effects. And then in the subsequent labs on digits and Cafe and Torch and Piano, you will actually train and build a network more completely and train a network from scratch yourself. There is a question on, are neural networks sensitive to the order in which the sequence of training samples are presented? The answer to that is yes, in some sense. Ultimately, your network, given sufficient training time, should converge to a similar set of features independent of the order, but there are some pitfalls that can actually occur if you don't take care about the order in which you put the data. One is that if you put in a highly correlated set of data first and then later on you'll be putting in samples which are very different but themselves correlated, you can find that your training can get stuck in what's called a local minima in optimization terms, and that's because you've basically overfit that first small sample of correlated data. And even if you don't get stuck in the local minima, training of the network, what we call convergence of the network parameters, can be slower if you don't have a randomized order to your data. So the best practice when you are training your network is that you randomize your input data before you put it into the network. And that only needs to be done once. It's not randomized for each iteration through the network.
John, this is Allison.
Hi, Allison.
Hi. I would say maybe one last question, and then we'll have to end the call for today.
Okay. So one question directly on image data here, which was asked a couple of times, was when you classify color images, do you input the RGB values directly, or are they encoded in some way? You can input the RGB values directly, and the convolutional neural network very naturally can apply to those 3 red, green, and blue valued images simultaneously. There are actually some transformations that people frequently make to transform the image into what we call YUV images, so luminance images, and you can actually get improved robustness to contrast variation, lighting variation, slight color variations by doing that. But certainly you can just input RGB values and get great performance.